Welcome to Phantastic Physics. Today I have a glass prism, a triangular glass prism, sitting on a bunch of random stuff, and all that stuff is just to give it some elevated height, because what I'm going to do is take this large flashlight with an incandescent light bulb, and I'm going to stand over in that direction and shine the light at this glass prism at an angle, and then something interesting will be projected onto this whiteboard behind me. So before I dive into the experiment, I'd like to remind everyone that if you go to the description of this video and click the link to the Phantastic Physics store, you will find a full year high school physics curriculum perfect for teachers, for students, for homeschool teachers, and for parents who want to help their kids get ahead in physics. Now, on to the experiment. This was originally done by Sir Isaac Newton in the year 1666. And this experiment actually proved that white light, or the light coming from the sun, is made up of several different kinds or wavelengths of light. And so I'm going to go ahead and turn off the lights and shine this light at the prism, and you'll be able to get a better sense of what will be projected on the whiteboard. Okay, so now that the lights have been dimmed, let's go ahead and shine this light and see what we see. Now, to make this work, it is important to hit just the right angle and just the right distance. I feel like I have a pretty good readout here. So if you look on the board, you can see red, orange, yellow, a little bit of green, blue, and then it goes to indigo, violet. So these are actually all the colors of the rainbow. It can be difficult to make out every single individual color, but you can see a nice strip of colors being kind of projected on the whiteboard due to this white light coming out of my flashlight, hitting this glass prism and passing through it. So what's causing this? What is the physics behind this rainbow effect? We're going to talk about that in just a moment. Okay, so how can we explain what we just saw? Well, when Isaac Newton did this experiment in 1666, what he noticed was when a beam of sunlight hit his glass prism, that sunlight, its angle changed. So as it entered the glass, it was coming in from this direction, it changed angles, and then what came out the other side were all the different colors of light. So what causes that? Well, it turns out that white light, or pure sunlight, is made up of lots of different wavelengths of light. So light is a spectrum, and in that spectrum, there are different wavelengths corresponding to each part of the spectrum. And so it turns out that red, orange, yellow, green, blue, indigo, violet, all the colors that we associate with the rainbow, each of those colors has its own wavelength of light. And so when that white light hits the prism, it's actually going to slow down. In fact, anytime a wave encounters a new medium, so in this case, when it's moving through the air and all of a sudden it encounters glass, when a wave encounters a new medium, it slows down and it actually changes direction by some angle. And that phenomenon is what we call refraction. It's the change of direction and the change of speed of any wave moving from one medium, like air, to another medium like glass. Now, where it gets interesting is, remember, that white light is made up of all the different wavelengths of the different colors. And because they're all different wavelengths, they're all going to refract at different angles. So when they pass through this prism, instead of all being together now, they are actually refracting in different angles, and that causes them to separate. So that phenomenon of separating the colors of white light is what we call dispersion. Dispersion is taking white light and separating it into its individual colors. And the reason dispersion happens, again, is because as white light passes through a new medium, every component of the light, so red, orange, yellow, green, indigo, violet, is refracting at a different angle, which causes all of them to exit at a different angle. And that causes the dispersion of the light that you see. Now, dispersion is also what explains rainbows. Because if you think about it, a rainbow is just right after it rains, there's a bunch of water droplets in the air, lots of water vapor. And so a water droplet, being made of water, is a different medium than the air around it. So when sunlight hits these water droplets, it passes through, and each color that makes up the sunlight is going to refract at a different angle and leave that raindrop dispersed. So all the individual colors have been separated. And so remember, there are millions of these raindrops in the air. And so the combined effect of all of those refractions and dispersions are what creates what we see as rainbows. Now, here's where it gets really interesting. So in the year 1800, William Herschel, another scientist who was playing around with light, he did the same experiment. He passed white light through a glass prism. It all refracted and dispersed the colors. And he had those colors like hit a boundary like this. And he was able to get nice, even strips of the colors, much better than I was able to do. And so he could see the red, orange, the yellow. Sorry, I don't have a yellow marker, so we're going to leave that blank. Green, blue, indigo, and violet. And just in case you're wondering about indigo, some people can't tell the difference between blue and indigo or indigo and violet. The only reason we named it indigo is because Isaac Newton really liked the number 7, and he wanted there to be 7 primary colors. So he made sure that there was a category called indigo. But remember, this is an infinite spectrum of, unlimited wavelengths corresponding to all the different parts of white light. So I could just as easily put a color between red and orange and call that red orange, or put one between yellow and green. He just happened to put indigo where it is. That was his preference. So we say there's 7 primary colors. It's really an infinite spectrum. But anyway, back to the experiment. So William Herschel separated the light. He had these bands, and then he did something really interesting. He had the idea to put a thermometer in each of these zones to try to see how much temperature was being accumulated in these areas to get a sense of how much energy was associated with each of these bands of light. And so he also had the brilliant idea of putting an extra thermometer out here outside of the red band. And he actually did this by mistake because he intended for this to be the control so that this could be like normal temperature and then he could compare that to the rest. But accidentally, it turned out what he found was that this thermometer ended up being significantly hotter than all the rest of them. So he went to check on the thermometers later, and he was shocked to see how hot this area was outside of the red zone. And what he concluded from that is that there's some other light beyond red that is invisible to the human eye. Because if there was nothing there, no energy there, there should have been no temperature reading on this thermometer. It should have been room temperature. And so he actually accidentally discovered what we call infrared light, or infrared. So infrared is beyond the red spectrum. It is the part of light so that the sun emits that we can't see. So any full spectrum white light will have all the colors that the human eye are able to detect, plus infrared light, which is beyond red. It's actually a different wavelength that's undetectable by human eyes. And so now today we know that there's even more invisible light. And in fact, the amount of light that human eyes can't detect far exceeds what we're able to see. So the colors that we can see coming from that prism represent just a small fraction of all the light that exists. And so if you go beyond infrared, what's that? Well, you get something called microwaves. Microwaves are very useful because we use them in microwave ovens to heat up food, and sometimes we use them for communications. And beyond microwaves, we get radio waves. So these are even longer wavelengths. So these are kind of like, these are different wavelengths here. As you move this way, they get longer and longer. As you go that way, they're shorter and shorter. So infrared waves have longer wavelengths than red, microwaves even longer, and then radio waves are really long wavelengths, like this. And then so this might be red, shorter wavelengths. And so radio waves, of course, are used for communications. Our cell phones communicate via radio, and lots of other devices. And then beyond violet, we know there's even more invisible light out here. So we get what's called ultraviolet, or also known as UV. So ultraviolet, of course, is what the sun produces that we are not happy to be exposed to. A lot of UV light is blocked by our atmosphere, but a lot of it does get through as well. And so we wear sunscreen to protect ourselves, because anything beyond the violet spectrum, once you get into ultraviolet, that has the potential to cause damage to your DNA. So we call this ionizing radiation. It's the dangerous kind, because the further out you get in this direction, the more energy that radiation carries. So we have ultraviolet. Beyond that, we have X-rays. And X-rays are even more high energy and more high frequency. And so X-rays are extremely dangerous. So they will cause great danger and great damage to your DNA structure if you're exposed to X-rays for any period of time. And then, of course, we do use X-rays to take dental scans or X-ray imaging, but those are very, very quick bursts of X-ray exposure. And you remember, you wear a lead vest during your dentist visit and when you're getting your bones X-rayed, because they want to limit the exposure to your vital organs, right? And then beyond X-rays, we have gamma rays. And gamma rays are extraordinarily high radiation, high frequency, high energy radiation, typically produced in cosmic events like supernovas and pulsars and things like that. So we're not really worried about gamma rays, at least on Earth. We're protected from a lot of that radiation from the sun. We're also protected from most solar X-ray emission. We do need protection for ultraviolet because it does get through the atmosphere. And these, of course, are not dangerous and can be very useful for technology. And of course, these are the ones we've adapted to see with the naked eye. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.